so I know a short turnaround time. We're looking at a majority multiple choice test. And I could see, 70 questions to like 80 questions, something like that. Not out of the ballpark. It's going to be like normal. You'll have an equation sheet. You'll have a periodic table. The new stuff will not be over representative. So everything should be covered relatively equally. And we also do have the policy. So let's say test 1, you got an 80. Test 2, you got a 60. Test 3, you got a 70. And on the final, you got an 80. Our policy, or my policy, is that if you do better on your final than your lowest scoring test, I will replace your lowest scoring test with the score you got on the final, since it is cumulative. If you do worse on the final, I won't bring down your lowest scoring test even further, though. But yeah, before we jump into our last material for the semester, any questions right off the bat? What's that? Anywhere from like 0 to like 4. Just because these tests, the turnaround time for me is also short for the final grade, so I generally don't like short answer on finals all that much. Any other questions? All right. So to remind you of what we have been talking about, we have been talking about entropy, which we give the symbol of S, and we said for a spontaneous reaction, the entropy of the universe must increase. That is the second law of thermodynamics. The universe is made out of 2 things. It's made out of your system, the thing you're watching, and it's made out of your surroundings, everything else that you are not measuring or watching. For chemistry, we generally say our systems are reactions. So anytime we see delta S reaction or delta S system, they mean the same thing. Now, for a reaction, if heat is released or absorbed, but we're going to talk about an exothermic reaction. If heat is released, that means it must be absorbed by your your surroundings. Right? So if heat leaves the reaction, it must go into the surroundings. So we had this mathematical expression, the heat of your surroundings is equal to negative the heat of your system, which is saying what this picture is representing, right? The heat of your system and surroundings are the same value, except one loses it, the other one gains it. That's what that negative sign is doing. It's making sure that the signs are different. Now, in our case, we generally are not doing work. And so since we are not doing any work, we get to say heat is actually this process called enthalpy. And this is stuff we talked about in General Chemistry 1 when we first introduced the idea of energy. If you don't remember that idea of what I'm talking about, that's totally fine. I just want you to know that when we see delta H, enthalpy, that is basically the same thing as heat. And so doing some derivations that I'm not going through, we can get to the expression that the change of entropy of your surroundings is equal to the negative delta H of your system divided by your temperature. And this was the last thing I talked about on Thursday. If you know the enthalpy change of your system and you know what temperature you are running your system, you know the entropy change of your surroundings, right? Entropy, enthalpy. And we're going to start off by doing an example question to look at how these mathematical equations actually work. But before we do, any questions about our review there of what we ended on with Thursday? All right. So we're going to jump into example 19.3 from your book, which is slide 246 on my giant PowerPoint. And we are given a reaction of propane gas combusting. So propane is C3H8 plus 5 moles of oxygen. Whenever we blow up carbon compounds, we always get carbon dioxide out and water. And we know that the change in enthalpy of this reaction is negative 2044 kilojoules. Now, the negative makes sense because we are exploding something, we are combusting something, and so heat is being released by the reaction. So that's where that negative sign means. This is exothermic. So I'm gonna walk you through how to do calculations for 19.3. Then I have another example for you to try. So the first question that is asked is calculate entropy change in surroundings at 25 degrees centigrade. So we want to know, okay, based on what we say here, is the entropy of the surroundings increasing or decreasing? So just before we do any numbers, let's just think about this like theory wise, because if you understand the theory and what's going on, that can help you making sure your numbers are correct when you do a calculation. So we have our reaction and it's releasing heat. And so that heat is being absorbed by our system, our surroundings. So without doing any calculation, based on just this setup, do you think the entropy of our surroundings increases? Or do you think the entropy of our surrounding should decrease if heat's being released to it? Right. So if heat is being released, entropy of our surrounding should increase. Remember, heat is energy. And so if we pump more energy into something, generally the entropy will increase. So let's actually see if the calculation bears that out. And so our equation for this was the change in entropy of our surroundings equals negative delta H of our system divided by whatever temperature we're running. And this temperature needs to be in Kelvin, right? If we were in Celsius, temperature could be negative. And that would throw all our calculations off if we were below 0. So the first thing we need to do is make that temperature into Kelvin. We can do that by adding 273. And so our temperature is actually 298 K. And so now we can calculate this. Delta S surroundings equals negative 2044 kilojoules. That was my delta H reaction. That was given. Divided by the temperature we are currently at, 298 K. And so the change in entropy of my surroundings, it's 6.86 kilojoules per Kelvin. Yeah, entropy has a weird unit, as a unit of temperature in the denominator. But that is how much the entropy has changed. And it has increased. So our intuition is right? If you release heat into your surroundings, the entropy of your surroundings should increase. And they do. So that's the first calculation for this problem. Any questions about calculating entropy change if given delta H and temperature? All right, let's do part B. Part B says, and now we're going to get into more chemistry intuition. B. What is the sign? Underline that. Of the entropy change for the system. What is the sign of the entropy change for the system? And the way this question is written out, no calculations, right? And in fact, we have not gone over any formula that can give us this. We will look at how to figure this out later today, but right now we actually can't calculate a number for this. So to figure this out, does entropy of our system increase or decrease? We have to go back to our chemical equation and look at what's going on. And so what we're doing to see if entropy is increasing or decreasing is that we are comparing reactants to products. And there's a few scenarios you could run into. And so I'm going to kind of give you the ground rules for the most common things you could run into. So let's just look at our situation here. So we have gas goes to gas. So since we're going from gas to gas, we can't really just look at these state symbols and know, are we becoming more ordered or disordered? What we can look at, though, is the number of moles of gas. So if you have the same state symbols happening in both your reactants and products, a quick way to determine delta S is look at moles. So on our reactant side, we have 6 moles of gas. On our product side, we have 7 moles of gas, or molecules of gas. What that is telling me is that entropy is increasing, right? The more molecules you have, and if you go back to our discussion of microstates on the end of Thursday, basically the more molecules you have, the more disordered your system is, the more ways there is to spread out energy. So that's there's more in-depth ways to do this, but this is like the very quick, easy way to do it. Now, if you are actually switching states, then it's easy. If you're going from liquid to gas, entropy is increasing. If you're going from a solid to liquid, entropy is increasing. If you're going from like solid to aqueous, entropy is increasing. So for state symbols, solid is the most ordered, followed by liquid and gas. Remember, aqueous means dissolved. If you are not switching which state you're in, just look at the number of moles of gas. And then eventually, we should have talked about it in this class, but we're not going to. But I'll tell you like how you would really do it. You would actually compare the number of bonds in each system. The system with fewer bonds generally has more entropy if the number of molecules are the same. But we're not going to dive into that right now. So, get back to my question. What is the sign of the entropy change for the system? It increases based on what we just said. I'll pull that up again. All right. Any questions about looking at a chemical reaction and knowing if entropy would increase or decrease based just on how the reaction is written? Like I said, I'll give you another example for you to try on your own, but questions on what's written up there. All right, the last part. Basically, what is the sign of entropy change for the universe? This one's easy. It's easy if you've done A and B. Remember, the change in entropy of the universe is made out of your system plus your surroundings. In part A, we said our surroundings has a positive value, positive 6.86. In part B, we said the system's also positive. So a positive plus a positive, well, delta S universe is positive. Which means, oh, this reaction is spontaneous as written. So propane gas will spontaneously combust, react with oxygen to create 3 moles of carbon dioxide plus 4 moles of water, based on our calculations of entropy. So any questions about example 19.3 there? All right, I have a question for you then. So I just said propane gas will spontaneously explode. I bet if I brought in a bunch of propane gas, like a tank of propane gas, and put it right here in front of the room, nobody would be scared that it would explode. How can I say it's spontaneous when we know if I have propane gas, it won't spontaneously explode? What piece of information from chemistry am I missing? How can it be spontaneous, but we know it's not spontaneous? Anyone have any ideas? Catalyst? Close. We don't need a catalyst. You need a spark. In chemistry terms, what do we call that spark? What does that spark give us? What's that? Well, that is the process of combustion. But for any reaction to happen, imagine that energy diagram where we have energy on the y-axis, reaction progress on the x. And if I draw that energy diagram, I have like a hump. What's that hump? Yeah, you need activation energy for any reaction. So the reason we call it spontaneous is that once you give it that activation energy, it doesn't stop. It will keep on going. In a non-spontaneous reaction, if I gave it activation energy, it would go and then stop. I would have to keep putting in that activation energy over and over and over and over again. So that's actually like a fine point of spontaneous. Like I said, spontaneous doesn't mean it will happen immediately. Like if I had propane gas, yeah, eventually it would explode. But not anytime soon. It would need that activation energy. Yes.
Right, so is the process spontaneous? So the
Yep.
same lighting modifier.
It's not spontaneous unless I give it activation energy. Yep. Once I give it activation energy, yeah, it would be spontaneous. All right, any questions about example 19.3? All right, let me give you one more. Just so you can get a handle on it. For practice 19.3. Like they say in med school, you see how one is done, then you do one, and then you teach somebody how to do it. That's how you learn stuff. You see it, you do it, then you teach it. So we have 2 moles of N2 gas plus O2 gas goes to 2 moles of N2O gas. Delta H for this reaction is positive 163.2 kilojoules. A, please calculate delta S surroundings. Temperature equals 25 C. B, sign of delta S reaction. C, sign of delta S universe. Is this spontaneous? So I'm going to give you a minute or two. It's basically the same question, just different variables here. If you have questions while doing this, just let me know. You calculate that. Right. Yep, but that is not the surroundings.
Yeah.
It would depend on the balance. Didn't have the positive. Alrighty. So let me start to go over this. So first off, we want to calculate delta S surroundings. Remember, our equation is delta S surroundings equals negative delta H reaction divided by T, which is negative 163.2 divided by 298. So the change in the entropy of our surroundings is 0.548 kilojoules negative per Kelvin. All right. Since this reaction requires heat, delta H is positive, it is drawing heat from its surroundings. So the surroundings are becoming more ordered. Entropy is decreasing. Now let's look at what's happening in the reaction. In the reaction, we're going from gas to gas again. Okay, so I need to look at the number of molecules. So my reactant, I have 3 molecules of gas. That is going to 2 molecules of gas. All right, that means our system is becoming more ordered, right? When you're going from gas to gas, if you decrease the number of molecules of gas, that means, oh, I'm becoming more ordered, which means entropy is also decreasing for my reaction. So our universe is made out of our reaction and our system. Or sorry, our reaction and our surroundings. I keep doing that. And our reaction is negative. Our surroundings is negative. So our delta S universe, the change of our entropy of our universe is negative, which means this reaction is non-spontaneous. All right. Any questions on how we did this sample problem? All right. If not, we can get into our next topic here. Our next topic is 19.6, which is Gibbs free energy, or how we actually determine if a reaction is spontaneous. And so kind of to start this discussion, I'm going to just write down the equation we were just working with spontaneity. We were looking at the change in entropy of the universe And remember, we said there positive equals spontaneous. And to calculate this, we needed to look at the entropy of our system plus the entropy of our surroundings. Now, this can kind of be a pain because your surroundings could be massive. And so it might be hard to do the whole entropy of the surroundings. So what I can do is I can actually say the delta S of the universe is equal to the entropy of our system. And we already have a mathematical expression for this. We said delta S surroundings equals negative delta H system divided by T. So I can plug that in. So now I can say, well, the entropy change of the universe, I can just focus on my system. I don't need to worry about my surroundings. If I know the entropy change of my system and the enthalpy change of my system, I can calculate delta H universe. And we can do some math here. And again, I'm kind of like skipping some logic steps, but what if I multiplied each side of the equation by negative T? Then what I would get is delta S universe times negative T equals, and I'm going to switch these, that equals delta H system minus T times delta S system. And so you might be asking yourself, why are we doing this? What's going on? Well, the change in the universe entropy multiplied by whatever temperature you're running your system, the negative temperature of that, we give that a special symbol. We call this delta G. This is called Gibbs free energy. In tables, in any reactions, the energy you are going to see is a delta G, right? And those of you going, I know since I teach biochemistry, those of you going to biochemistry, I speak strictly in delta G's. I never bring up delta S universe. You only talk in delta G. And so Gibbs free energy is equal to the change in enthalpy minus temperature times change in entropy. So this equation is like one of the key equations in all of chemistry. No matter what field of chemistry you go into or use, this equation will probably pop up because it allows us to determine if a reaction is spontaneous. So, kind of going back to our talk of delta S universe, we said for a spontaneous reaction, we said delta S universe is positive. But let's look at delta G. All right. We said delta G is equal to delta S universe times negative T. So if a spontaneous reaction has a positive delta S universe, What must be the sign of delta G to be spontaneous based on that math? Has to be negative. So for a spontaneous reaction, delta G is negative. The signs flip, which is confusing when you first learn this. But that's why they flip. It's based on the math. Therefore, for a non-spontaneous reaction, delta S universe, well, that's negative. And so delta G is positive. Then if you're at equilibrium, both delta S universe and delta G equal 0. And so for me, something I'd like to hammer home when we get into higher levels when I teach biochemistry, negative energy is a good thing. Because we only talk about Gibbs free energy. So if you lose Gibbs free energy, that's good. That means your reaction is spontaneous. If you gain Gibbs free energy, that's generally bad because you're not spontaneous anymore. But yeah, that is moving on. In all of chemistry, basically, we're not going to bring up delta S universe again unless you are one of the lucky few who are a chemistry major, then you get to take physical chemistry. But I will be talking about delta G from here on out. All right. Any questions about delta G here, about Gibbs free energy or its relationship to delta S universe? All right, let's just do one problem that we can just calculate delta G just to try it out. So this is question 104. And by the way, there is question 103 as extra practice. We're not going to do that in class, just to make sure I cover what I need to. But that is there on the slides for you to try out to make sure it basically looks at how G, H, and S are all related. But question 104, we'll just do one of them because if you can do one, you can do them all. Delta H reaction equals 115 kilojoules. Delta S reaction equals negative 263 joules per Kelvin. Temperature is 298 K. Please calculate delta G for me. And tell me, is this reaction spontaneous? Spontaneous or not? So just give you a minute or two just so you can get your hands on that equation. Those of you in class, I will lay out the exams on the little podium over there. And when we take a break here in like 10, 15 minutes, feel free to grab it then. It does not matter if Gibbs is in joules or kilojoules, as long as you are consistent with your calculation. All right. So delta G equals delta H minus T delta S. So this is equal to 115 kilojoules minus 298 times negative 0.263 kilojoules. All right. So the thing you need to look out for is that both H and S have to have the same units of energy. It doesn't matter if you make H into joules or S into kilojoules. You just have to pick one, but they do have to be the same unit. So 115 minus 298 times negative 0.263. Delta G equals 193.37 kilojoules. Delta G is positive. That means not spontaneous. Remember, for delta G, negative energy, good. All right. So questions about Gibbs free energy here. All right. So let's go on to chapter 19, section 0.8, which is talking about standard free energies. And to me, standard free energies, one thing it's really good at is comparing different reactions. Right? Because when we calculate delta G, it's actually based on a lot of things. So delta G is like based on temperature. It's based on the amount of product and reactant. I guess it's not a lot of things, just a few things. But since delta G is based on how much product and reactant you have at any given time, imagine, and again, I'm going to go back to my biochemistry roots. Imagine we are looking at like metabolism. We're looking at reactions inside the cell. And I have reaction 1 and I have reaction 2. I want to know which one is more favorable. And that's not easy to do if I'm looking at delta G, because inside the cell, the amount of reactants and products are constantly changing. So at any given time, different reactions could have different delta G's. So that can be a pain in the butt sometimes. So one of the things we do is that we have a different delta G we talk about. And this is our standard free energy. And when we talk about standard, we already looked at this symbol before, we get a little circle. Again, this is called like a knot. Or a knot. So delta G knot is equal to delta H knot minus T delta S knot. So when we have this knot, we are saying we are under standard conditions. And standard conditions is a definition of our current system. And so if I say we are working under standard conditions, what I'm telling you is that we have 1 mole of compound. Actually, sorry. Let me break it into each part. We have, if you are working with solids, you are at 25 C, 1 atmosphere, and the amount of stuff you have is 1 mole. I'm telling you, okay, it's 1 mole of solids. If we are working with liquids, and this includes anything that is aqueous as well, we are at 25 C. Our concentration is 1 molar. If we are working with gases, we are at 25 C. The pressure is 1 atmosphere, and we have 1 mole of material. Right? So this gets around the issue of delta G changing with temperature and with delta G changing about how much reactants and products you have at any given time. Because I'm telling you, everything's just 1. I'm saying standard, we know what it is. Now I can directly compare 2 reactions. I can compare reaction 1 to 2 and just say which one is more favorable if I set these conditions to be standard. And so a lot of the times when we look at reactions in like textbooks and papers or wherever, the delta G you're given is delta G naught. You're not given like real delta G because it just changes so much based on conditions. All right. So we will look at an example problem with this. But before we do, any questions about just the idea of standard states? The big thing is you want to remember everything is like 1 mole in 25 C. That's the 2 things that really matter. 1 mole and 25 C. All right, let's do example 19.6. This will be another one that I kind of like walk you through. And so we have the reaction NO plus 1/2 O2 goes to NO2 gas. And we are given, the question is, what is delta G naught at 25. Is this spontaneous? And then we're given a bunch of information. We're given a table that has these things called delta HF. And we're given these things called SO. This is kilojoules per mole. This is joules per mole K. And then we're given all the compounds we care about. So O2 has a delta H formation of 0. Delta S is 205, whoops, 205.2. NO, these are all gases, but I'll put that. NO gas has a delta HF of 91.3. And S of 210.8. And then NO2 is 33.2 and 240.1. All right, so let me just briefly talk about what these things are. So that F, that stands for formation. Basically, what that says is when we first create this molecule, if I create O2, how much heat is absorbed or released? If I create NO, if I create NO2, and this is a topic that was brought up back in General Chemistry 1, but we are revisiting it here, and I'll walk you through how to use these again. S, we've already talked about. It's just O2, how much entropy does O2 itself have? How much entropy does NO have? How much entropy does NO2 have? And this is all the information we need to calculate our problem. Because we have delta G equals delta H minus T delta S. All right, so my question for you is, I keep saying this delta. What does delta mean again? Change. What is change in chemistry? How do we calculate that? Final minus initial. What's our final in chemistry? So delta in chemistry is going to be products minus reactants, right? Because delta is change. Change is final minus initial. Chemistry, our final is our products. So let's calculate delta S. So delta S naught. And this is how we do it. So we have 1 mole of product. So I'm going to do 1 times our product is NO2. So 240.1. So it's the number of moles of products multiplied by my delta S of my product. And I'm going to subtract that by, so let me do my reactants. Let me color code it. So if you're looking back today or tomorrow, products minus reactants minus, okay, so we have 1 reactant of NO, so 1 times NO is 210.8. And I'm going to add that to, because we have two reactants, so I need to do addition. I'm going to add that to 1/2, because we have 1/2 mole of O2 times 205.2. And that will give me the delta S of this reaction. If I know the entropy of my products and my reactants, delta S is relatively simple. So this is 240.1 minus 210.8 plus 0.5 times 205.2. And so the change in entropy of our reaction under standard conditions, delta S naught, is negative 73.3 joules per mole K. And one thing that as students, you want to start training yourself to do is whenever you do a calculation, try to tie that back to logic. According to our reaction as written, does it make sense that the change in entropy under standard conditions is a negative value? Would you expect it to be a negative value? Based on what we said, I don't know, 25 minutes ago? How do we determine if delta S should be a positive or a negative value for a reaction again? Sure, delta S is negative. My question is, does that make sense? How can we predict without doing any math if our reaction should have a negative entropy or a positive entropy? What should we look at again? Yeah, the number of moles of the gas and the products or reactants, right? We're going from a gas to a gas. And so the moles on the left-hand side are 1.5. The moles on my products are 1. Oh, entropy should decrease. It does. So we probably did our calculation right. Right, questions on how I got delta S naught, or questions on that idea of logic? So the way to kind of like make sense of that is thinking entropy is chaos. So if chaos is decreasing, my system is becoming more ordered, which is not favorable. The universe loves disorder. So let me think. It all comes down to microstates. For those of you watching at home, I have 2 molecules of gas. So I have 2 molecules of gas. And imagine, actually, I'm going to draw this out. Why am I having props? So I have 2 molecules of gas. I have a red gas and I have a blue gas. And I have a system. My system is 4 quadrants. I'm going to make it super simple. And I can put in one box, only 1 gas molecule can go, right? So here's one system. I have gas molecule red here, gas molecule blue here. So that's one possibility. Okay. And another possibility is red molecule here, blue molecule here, right? So that's another possibility. So on and so forth. So the number of possibilities of placing these two molecules in this box, does anyone actually know that number? How many possible ways can I do this? I don't think it's 16. Because if red's here, there's 3 ways I can put blue. So that's 3 different possibilities if red's right here. If I move red to this quadrant now, I can move blue in 3 other different ways. If I put red down here, I can move blue in 3 different ways. If I put red in the bottom left, I can move 3 different ways for blue. 3, 6, 9, 12. There are 12 possibilities I can arrange this system. All right, let's do the same idea, but instead, I only have 1 atom, red. How many different ways are there to arrange this red atom in this system? There's only 4. All right. Which has more microstates? The system with 2 gas molecules or the system with 1 gas molecule? 2. Therefore, entropy is higher in the system with 2 gas molecules. That's all entropy means. The different ways I can arrange a system. The more ways there are to arrange a system, the higher the entropy, or the more disorder I can create, the more chaos. That's why I can simply say, look at the gas molecules before and after. If you went down, entropy must decrease. That makes sense? And by the way, entropy is one of those things, just kind of going on a tangent. Physicists still struggle with the definition of it. It's such a complex concept to like actually fully understand, but that's the beginnings of it. Comes down to microstates. All right. Please calculate delta H naught for me then. Based on what I did for delta S. See if you can follow along for delta H naught. All right. So delta H is the same idea as delta S. You do products minus reactants, but you have to multiply your products by how many moles you have. And actually, I should have... No, I can keep that mole there. Never mind. So delta H is... So our product is NO2. So we have... I'm doing H, yeah. So we have 1 mole of NO2 times 33.2 minus 1 mole of NO, which is 91.3. So multiply by 91.3 plus 1/2 mole times 0, because oxygen has a formation of 0. So delta H is 33 minus 91.3. Delta H is negative 58. Canva, don't die on me quite yet. 58.3 kilojoules per mole. And now we have all the information we need to calculate delta G. Delta G is equal to delta H, okay, negative 58.3 kilojoules per mole, minus T, our temperature is 25, which is 298 Kelvin, multiplied by S. Remember, S and H have to be in the same unit, so that's negative 0.0733 kilojoules. And so delta G for this reaction is negative 36.5 kilojoules per mole, which means this is spontaneous. So even though the entropy of our system is decreasing, it is releasing so much heat that overall Gibbs free energy is negative, or overall the entropy of the universe must increase. Those are saying the same thing. Question about our calculation. Right. I'm going to leave this up if you want to look at it. Otherwise, we'll take our last break of the semester. Let us come back at 9:23. Take our little 10-minute break. Again, your tests are up there. Feel free to grab them. Yeah, get your snacks, stretch. And then we'll finish our discussions on G. Hopefully talk about batteries a little bit. Yeah, we won't have time for that. Yeah, basically whatever we get to today. Hopefully we'll cover all that electrochemistry stuff. But if we don't, whatever we get to.